Carnegie scientists explore the outermost reaches of space, the mysterious depths of the Earth, and the origins and mechanisms of life. Our brilliant and dynamic teams of scientists transform the landscape of discovery with their unbridled passion, insatiable curiosity, and never-ending quest for knowledge. With limited teaching, administrative, and grant pressures, Carnegie's scientists concentrate on research and are empowered to go their own way. Our scientists are chosen for unique skills and boldness. Their amazing discoveries, spanning more than a century, demonstrate the power of freedom. Carnegie investigators are intrepid adventurers who pursue their goals even as they mentor and train the next generation of scientists. They are free to question, to wonder, to creatively pursue ideas from the vast universe to the subatomic world. Our scientists redefine the pursuit of what's possible for us, our planet, our universe. We explore the past to understand the present and inform the future.
Good evening, everyone, and welcome. I'm glad you came through the storm to join us tonight. We're going to be talking about a different kind of storm tonight, a geological storm instead of the meteorological storm. It's only recently, maybe in the past 50 years or so, that scientists have understood enough about the dynamics of volcanoes to try to forecast eruptions, and we're working toward being able to cause them selectively in interesting ways. Haven't gotten there yet, but there have been many successes in early detection, and some lives have been saved, which is great, but it remains an imperfect science. Volcanic activities and the eruptions themselves require intense analysis before, during, and after, ideally, major events, which requires monitoring systems, rapid response systems, and so forth. We have to understand the probabilities of different possible outcomes in order to guide reactions at times of potential crisis. It's very important. And 10 or 20 volcanoes erupt every day on Earth, none of them in this neighborhood, just to not get you concerned. And that's a daunting thing to face because quite a few volcanoes are in places surrounded by fairly dense populations. There are whole cities built on the sides of volcanoes, and you really need to keep on it to deal with good decision-making in response to threats. The odds of useful predictions improve due to persistent investigations of the fundamental geological aspects of the eruptions. And our guest tonight, Diana Roman, has made important strides in the last few years in this area. She's been a staff scientist at Carnegie's Department of Terrestrial Magnetism here in Washington since 2011. At DTM, she studies the mechanics of how magma moves through the Earth's crust under your feet at this moment, determining how this movement responds to changes in seismicity and tectonic stress. She has developed techniques for monitoring active or restless volcanoes by analyzing high-frequency volcanic seismicity. She also studies the seismicity of quiescent volcanoes and explores the nature of volcanic intrusions, what she calls failed eruptions. She came to geology from a typical background. She was in the financial world. She was 2 years after receiving her bachelor's degree from Cornell. She was an analyst at Barclays Global Investors, which all of those people always come into volcanology. In 1999, she left that world, earning her master's degree and later her PhD in geology from the University of Oregon. For 5 years before joining Carnegie, she was an professor of geology at the University of South Florida, where in 2007 she received the university's Outstanding Research Achievement Award. A year later, she received the George Walker Award from the International Association of Volcanology and Chemistry of the Earth's Interior. I've had the pleasure of watching her in action. Last year, I joined her and another of our scientists who's with us here tonight, another DTM scientist, Blair Wagner, on a field expedition in Nicaragua. And I thought the easiest way to tell you about that was to put together a little movie that I made from that trip, which is just a few minutes long, and we'll start it in a second.
So we're just getting our first look at Tolica Volcano, which you can see off in the distance behind us, smoking away. I've been working here for a little over 7 years. I have instruments all over this volcano, including seismometers, and a colleague has some instrumentation that measures the deformation of the Earth's surface, and we've been trying to understand the activity of this volcano through analysis of those measurements.
We're standing here at Masaya Volcano, just outside of Managua in Nicaragua. This volcano is part of a larger chain of volcanoes that reaches from Mexico all the way down to the southern tip of South America. And that's the southeastern rim of what's known as the Ring of Fire, which goes all the way around the Pacific. These are a series of volcanoes that are caused because the oceanic plate is sliding down underneath the continent, in this case, the Central American subcontinent. The downgoing oceanic plate brings water with it into the mantle, and once it releases that water, when you add water to hot rock, it melts, and that melt makes it to the surface in the form of these volcanoes.
Volcano, which is, you can't actually really see from where we are, is the oldest structure. It's about 10 kilometers across and 5 kilometers wide. And then within it are several smaller volcanoes we call cinder cones, and we're at the top of one of them right now. This is the youngest cinder cone in the Masaya caldera, or in the crater of the oldest, largest volcano. And beneath us is actually a series of pit craters formed at different times. The current crater below us is called Santiago Crater. It's about 350 meters below us, and the crater here is about ½ a kilometer. So it's actually fairly small compared to the size of the entire volcanic edifice. But it's still a pretty massive site, and there's quite a bit of lava down there.
So that was just as amazing in person. I mean, it was incredible. Looked like it had the low viscosity of, a hot tub or something. And we didn't try that. And we didn't see Gollum anywhere, for those of you who are wondering. It's fascinating, of course, to be in the field with scientists. They were working very hard. I was taking movies and pictures. They're lugging, 40-pound packs of seismometers up mountain slopes and so on. I'm carrying a camera. It was a good deal. But it's fascinating, of course, to hear them tell the stories of what's beneath our feet, and that's what we're about to hear from Diana today. So welcome. Thanks for joining us.
All right. Thank you, Matt, for that introduction and the video. We had a really great few days in Nicaragua together. So thank you all for coming on this first beautifully sunny and then suddenly very rainy evening. I really appreciate it. So I found it kind of funny that they chose this picture of me to advertise the talk. This was actually a day off when I was visiting the Hawaiian Volcano Observatory a few years ago, and there was a nice day when we didn't have too much work, so we decided to hike out to the active lava flows and just poke at them for a while, because who wouldn't want to do that? So this is actually not at all what it looks like when I'm out working on a volcano. This is a little bit more accurate. You can kind of see why they chose the first picture. So this is typically me on a volcano. Matt saw some of this, I think. And I'll get to what I'm doing in the hole in a few slides. But I first want to say a few words about why we study volcanoes, why we care about them. And the first one, and Matt certainly did a great job of conveying that, is that volcanoes are fascinating natural phenomena. Throughout human history, they've been a source of inspiration for art, the works of J.M.W. Turner, and mythology, the legend of the Hawaiian goddess Pele. And every time, these are just a few pictures I've taken in the past few years of things I've seen in the field. And I've been doing this for almost 20 years, and every time I see a volcano in eruption, I'm overwhelmed with wonder at this process and this phenomenon. So another reason is that volcanoes are a unique feature of, active volcanism is a unique feature of our planet. Volcanoes are on every continent except Australia, and maybe even there's some remnant volcanism there, and throughout the ocean basins. And we understand that they're the result of interaction between the Earth's tectonic plates, the crust, with each other, and also interactions between the plates of the Earth's crust and the underlying layer, the Earth's mantle. We know that there are basically three processes that produce volcanism on Earth. The first is subduction, where one plate dives underneath another plate. So this is the process that drives volcanism in places like Alaska and the Cascades throughout the Pacific Northwest. As that plate gets to a certain depth, it undergoes a chemical reaction and releases magma that then makes its way up and forms these arcs of volcanoes. They're the most explosive volcanoes on Earth. Another type of volcanism is hotspot volcanism. So Hawaii is an example of hotspot. This is a place where a deep-rooted plume of magma from somewhere in the Earth's mantle rises through the crust and creates chains as the crust moves over this stationary plume. And then the third type is mid-ocean ridge or rift volcanism. So, for example, the volcanoes in the East African Rift are a result of the Earth's crust being torn apart slowly, and this is a way that magma can leak through the crust and onto the Earth's surface. So, deepening our understanding, this understanding of how volcanoes form and how they work is one of the main goals of my field of volcanology, and one of the reasons we're interested in volcanoes. The third reason, and the one that will be the focus of tonight's talk, is that volcanoes are dangerous. And a main goal of volcanology is to minimize or mitigate this danger by providing adequate warning that a volcano is going to erupt so that people can be moved out of the way. We can't stop an eruption in just about every case, but we can warn people and get them to a safe distance. So this is a fairly complicated plot. There's a lot of information on here, but I basically want you to take two pieces of information away from it. The first of which is that the largest events, the super eruptions on Earth, so this is the Yellowstone eruption or the Campiflagre eruption, compared to other natural events at their largest, so like the largest earthquake that's possible, the largest volcanic eruption on Earth can do much, much more damage than any other natural phenomenon. So while the largest earthquake that's possible will certainly affect produce a devastating effect on a region of our planet and potentially even an entire ocean basin, it's only volcanic eruptions at their largest that can cause global catastrophes and mass extinctions. And this has happened a few times in our planet's history. So that's the bad news. The good news, and the second thing I'd like you to take from this plot, is that these guys are quite rare. So what you're seeing here is the chance of occurrence in any given year. And like all natural phenomena, it's far more common to have very small eruptions, so down here with sort of small damage, a St. Helens or a Vesuvius, which to us is actually even kind of a moderate size eruption, than it is to have a super eruption. So this is why, despite what you might read to the contrary, we're not expecting a cataclysmic eruption of Yellowstone anytime soon. And in our lifetime, basically what we have to deal with is small-scale volcanic hazards, so this end of the plot. So let me say a few words about what constitutes small-scale volcanic hazards. So certainly an eruption, a minor eruption, poses a threat to people who are within the immediate vicinity of that volcano. But actually, the greater exposure for small-scale eruption is to aircraft. And that's because even though many of Earth's volcanoes are incredibly remote, nobody's living anywhere nearby, they often underlie major air traffic corridors. So as an example, illustrated up here in the top left, anytime you take a flight from anywhere in Eastern North America, Chicago, Boston, New York, DC, to anywhere in Asia, Beijing, Hong Kong, Tokyo, you're going to take a Great Circle route, which takes you up and over this chain of volcanoes here in Alaska, the Aleutians, the volcanoes of the Kamchatka Peninsula, and the volcanoes of the Kurils. These are all incredibly explosive, active volcanoes. So this is one of the heaviest trafficked air corridors on Earth. So fortunately, there's a very good system in place to prevent aircraft ash encounters. So the point is, jet engines don't particularly like volcanic ash, which is not really an ash. It's tiny glass shards, and it really doesn't play well with jet engines and other important pieces of a plane. So there's a system in place, the VACs, that constitute a set of 24/7 watch offices who are fully responsible for different sectors of the globe. So we have one here in DC that watches this part. Basically for rapid dissemination of information to pilots to basically get out of the way. So there's a lot of rerouting or turnbacks that happen, and it works so well that you probably wouldn't even know about it in most cases. If it happened to you, you might take a slight diversion. So this works well even on volcanoes that are not instrumentally monitored. And in fact, these guys are pretty good at this point, but many of these volcanoes, and in fact in the Kurils, are completely unmonitored. So the key to this system is basically detecting that ash cloud the minute the volcano erupts, and even giving a few minutes, a little bit of warning to divert an aircraft. So that's good, but the far better situation would be to have an advance warning that the volcano is getting ready to erupt, so to basically reroute air traffic and make longer-term plans if a volcano is likely to erupt. And this brings me to one of what certainly to me is the coolest things about volcanoes, which is that if we're listening to them correctly, they give us warning in just about every single case that they're going to erupt. And that warning varies anywhere from hours in a rare handful of cases to decades at some volcanoes. And we're pushing this boundary constant. It's typical now we see weeks to months, but again, we're pushing, and I'll talk about this a bit, we're pushing these so that we have more and more advanced warning. And this makes them unique compared to other natural hazards, some of which do have precursors, do have warnings. So hurricanes, we can see them as they form from weather satellites, and we can predict their paths and their strength. But really only generally days to hours, and in some rare cases weeks of warning compared to the longer-term warnings we get. Some natural hazards don't even have precursors. So for example, earthquakes. We have absolutely no tool to sense that an earthquake is coming. There are no known precursors to these events. Okay, so what do I mean when I talk about precursors? What are the types of things that we can look for that will give us an indication that our friendly neighborhood volcano is getting ready to erupt? And there are lots of them, but I'm gonna describe the three big ones to you. The first common sign that a volcano is getting ready to erupt is that the ground starts to deform. And it's very subtle, and by subtle I mean millimeters to centimeters of ground movement. Not something you would be able to sense with your eye, with walking around. The way that we detect this subtle motion is using either very sensitive GPS receivers that we put on points on the ground and track the position of the points, and we can get millimeter scale accuracy. We can also do it from space, and actually one of my colleagues here in the audience, one of our newest hires in my group, is an expert in satellite monitoring of volcanic deformation. So we have instruments that are basically radars that are borne on satellites that orbit the Earth and take pictures at different points in time, and by comparing those pictures over time, we can see very, very subtle deformation of the ground. Another major tool is gas emission. So volcanoes, before they erupt, will often increase the amount of gases that are coming through the vent or through fumaroles or cracks on the flank. And these gases are usually things like sulfur dioxide or hydrogen sulfide, it's a stinky smell, but also carbon dioxide, which is a little bit more difficult to detect because it's a high concentration already in the atmosphere. So we tend to focus on the sulfur species. And again, we can do this. We can measure these from sometimes actually smelling them, but using ground-based instrumentation. There are satellite sensors as well, and sometimes we just duct tape the sensor onto a helicopter and go up for a sniff if conditions allow. It's actually a really nice way to get a good sense of what's happening up there. And then the last one, and actually the most common precursor, in part because this is the most common way of instrumenting a volcano, but in part because it's very reliable, is seismic activity, so increases in the seismic activity of a volcano. And this is what I do. So this brings me back to what's Diana doing in that hole. So my team conducts opportunistic studies of volcanic activity worldwide using volcano seismology. So my field is volcano seismology, which is the study of ground vibrations produced by volcanoes. So up on the left here is a map with the little triangles showing you all of the places that I've worked in my career. My main stomping grounds are Alaska and Central America, but I've really kind of worked all over the place. And one of the interesting aspects of my field is that we kind of have to react. We can't turn a particular volcano on and off to do an experiment. So we kind of have to react to what Earth gives us. So you'll see this in that I kind of jump around both in terms of field location, but also the types of questions I study because it's very much, whatever information we can get depending on what activity is happening and where we have a data source. So our data comes from, we get our data in two different ways. The first of which is instrumental campaigns where we'll actually go out to a volcano and install seismometers and keep them running for as long as we can. Typically when we do this, it's on a volcano that's already in some sort of long-term eruption or unrest. And so this is a recent experiment in Mexico, and my colleague Oscar drew whole duty that day, so I finally got to stand up and look around. The other way that we get our data, and actually a really important way for the types of studies I'm going to talk about tonight, is through partnerships with governmental monitoring agencies. So countries that have active volcanoes generally run another 24/7 watch, so collecting continuous instrument data and analyzing it to try and see an eruption coming. And so this data is a very rich source for researchers like myself to go back into the sort of do a post-mortem after something has happened to see, are there any things we could be doing better? Are there any signs we missed? And the reason for this is because generally when I do a study, my funding only allows me to keep instruments out for maybe a year or two, and we can usually only go once a volcano is erupting. So this is our only way of doing long-term studies and also looking at the pre-eruptive seismicity. So these are very important partnerships. Okay, so one way or another, somebody puts a seismometer in a hole. There's a picture of one. We really like the Home Depot buckets. You can buy them in lots of different places. It's amazing. We're trying to sense, so this is a seismometer here, and it's incredibly sensitive, and we're trying to pick up minute ground vibrations. So we try to get it as well coupled into the ground as possible, and this is one of the reasons that we bury them, and here we've put it on some concrete and so on. So seismometers go in the ground, and then ideally, and far less frequently than you would hope, we come back and see that it has recorded some seismic data. So this is an example of our raw seismic data, and you can read this kind of like a book. So each line here is raw seismic data over about 30 minutes, and I think there's a few days on this plot. And so this is basically just a time series of the amplitude of ground vibration. And in this raw form, it's not terribly useful or meaningful to us. And the way in which we reduce it really depends on what we're interested in, what questions we're trying to answer. But there are generally three things that we look for in the data. The first is changes in the event rate and changes in event rate. So you can see these little pops in here. These are all little tiny, tiny earthquakes. This is St. Helens data. So one of the first things we do is we process this data to pick out all these little pops, and then we count them and we see if their rate is changing through time. if we have enough instruments on the volcano in the right place, and we can record one of these pops from multiple positions, we can triangulate and figure out its location and its depth. And so tracking changes in the location and the depth of the earthquakes is also a very important tool for us. And the third thing that we look at typically is changes in the frequency content of the earthquake. So I want to spend a little bit of time explaining this because this will be important throughout the rest of the talk. So what I mean by frequency content, so when I say rate, it just means like number of events per hour. When I say frequency, I'm talking about the distribution of energy in the waveform of the seismic event. So you're seeing a few examples here. I'll tell you how to look at these data. So this is raw seismic data here shown as time on the top. These are the top plots, and then some measure of just amplitude of ground vibration. On the bottom here, of each, these little colorful plots are again time on the x-axis, but in this case, the y-axis is frequency, or pitch for musicians in the room. And the hot colors tell you at what frequency most of the energy in that vibration is distributed. So the reason we're interested in this information is because volcanoes produce a wide range of seismic event types. Two of the most common are shown here. One is a high-frequency earthquake, or we call them a VT earthquake sometime. And they have most of their energy above 5 hertz. So to us, to a volcano seismologist, that's high frequency. So that's well below the range of human hearing. But if I were to speed it up a little bit and play it for you as a sound, it might sound a bit like, I'm going to date myself here, Mariah Carey or soprano. Another really common type of seismicity that we record on volcano is the long period or low frequency event. And these are events where most of the energy now is below 5 hertz. So if I were to speed this up in the same way and play it for you, it would be Barry White. Okay, so we have Mariah and we have Barry. And then also our seismometers pick up anything that happens on the surface. So we see rock falls, we see debris avalanches, we see shaking from explosions. And we can mine all of these different signals for information about the volcano. Okay, so the reason that we look at these things, rate, location, and frequency, is kind of summed up in this next figure here, which is sort of a cartoon of how magma might move through the crust up to the surface before an eruption. Okay, so here's magma making its way up, and then boom, we have an eruption. And so if we were to think about what kind of earthquake activity might accompany that process, we'd expect from nothing to magma starting to have to push its way, push rock out of the way, having to break that rock. And so we'd probably see some deeper events, higher frequency rock breaking events. So we'd expect maybe a change in the number of earthquakes over time, increase in the number of earthquakes, and also a decrease in their depth over time. So those are two kind of intuitive things that might let you predict an eruption. Another one is a changeover from high frequency, from Mariah, to low frequency Barry. And the reason for this is that magma is liquid rock, but it has gases dissolved in it. So it's like a bottle of Diet Coke. So as that magma gets closer to the Earth's surface, and the pressure on that magma is reduced, that gas starts to come out of solution. So it's just like when you take the top off your Diet Coke and you can hear the gas coming out. Magma does the same thing. So magma that's shallower, that's closer to the surface, is going to start releasing gas. And as that gas moves through cracks in the rock, it'll start to set up little vibrations, and this is more like a resonance. It's like blowing air through a flute or an organ pipe, and it produces low frequencies. And so this is a sign for us. When Barry White shows up at your volcano, you know things are about to get real. Okay. So there are examples of eruptions that very nicely follow these patterns. So one example of a changeover from high-frequency seismicity to low-frequency seismicity in a precursory sequence comes from the most recent eruption of Mount St. Helens in 2004. So again, you're looking here at time on X, and then this is frequency on Y. So high frequency up here, low frequency down here. The eruption started right around here, and you can see really nicely that the first seismicity, this is some noise here, the first seismicity earthquakes were high, and then it transitioned over to low before the eruption. So this is kind of consistent with that model. Another example that demonstrates that nice shallowing of seismicity, so the earthquakes tracking the magma, upwards towards the surface comes from a volcano called Piton de la Fournaise, which is in the Indian Ocean on an island called Réunion. It's a French territory and a really lovely place. So here, what you're looking at are little snapshots through time. So time going that way, and each one of these windows is a representation of the earthquakes during that time window in 2 dimensions, so depth and then longitude. And if you look through time, the black guys are the current ones, and then the gray guys are the previous ones. You can actually see really nicely how this seismicity is kind of tracking upwards, and then basically almost makes it to the vent when the eruption starts. So this is a nice upward propagation. So these are well-behaved volcanoes. They produce precursory unrest that's very consistent with our intuitive idea of how magma assembles and ascends before an eruption. So what I tend to focus on in my research are the bad boys, the ones that don't follow this pattern. And that's because those are far more difficult to forecast. And it's not to say that they aren't forecast, and I think all of the examples I'll show you today were successfully forecast by their monitoring agencies. But they're confusing and difficult, and we want to understand them more and develop better tools that might be more appropriate. So I'm going to show you 3 stories. Basically examples of volcanoes that in some way violate these patterns. Actually, 2 of them will violate the pattern. And I'll talk about some new tools that we've developed to try and understand the volcanoes we worked on and other similar volcanoes. Okay. So the first story I want to talk about has to do with this idea of earthquakes moving upwards towards the surface. So I'll call this bottom-up seismic propagation. So just like Piton de la Fournaise in the last slide. So we don't actually have a whole lot of data sets where we can look at this, but as we accumulate more, it turns out that that nice behavior is actually very rare. And in fact, most of the time, what we observe is the opposite, which is top-down seismic propagation. So here's one example from Merapi volcano in Indonesia, which had a major eruption in 2010. So here you're looking at time. The eruption is here. Each one of these green dots is an earthquake with its depth over here. So these are time depth plots. So the seismicity before the eruption really kind of got going several months before, but really only got going around here. And the very first earthquakes that were recorded were quite shallow, and in fact, if anything, kind of deepened through time. And we have geochemical evidence from the products of this eruption that that magma source was actually located somewhere well down here in the crust. So for some reason, we aren't seeing that expected pattern. So here's another similar example from a volcano in Alaska called Augustine, which erupted in 2006. So the eruption is here. And then these are the earthquakes going back a year. We think that the seismic unrest, the immediate precursory seismic unrest of this eruption started around here. So Augustine has a bit of a background kind of crackle, and then there was an uptick in the rate here. So, but even then, the earthquakes that we saw leading up entirely through the eruption were all just beneath the vent of this volcano. And again, we know geochemically that the source for this magma was down here. So this is not necessarily a problem because there still is precursory seismicity. It's weird, but it's also an opportunity because it implies that there may be a period. So we tend to take the onset of strong seismicity as our first precursor, but it implies that there may actually be a period before we start seeing those earthquakes where magma is ascending. So we might actually be able to look with some new tools in that period and find earlier indications that an eruption is coming. So we got interested in testing this idea to see if this would be a useful way to monitor these volcanoes. And for our study, we focused on another Alaskan volcano called Redoubt. It's about 70 kilometers from Anchorage. So it's remote, but quite a bear for air traffic in the area. It erupted in 2009 most recently, and that's the eruption that I'll focus on, and then also had an eruption in 1989. The 1989 eruption actually only had, it was well monitored, but it only had really about 1 day of precursory seismicity. So this volcano in particular, if we can find anything that's a clue before that seismicity starts, would be important, because 1 day of warning, while sufficient, is not a lot. So, so here's the time depth for Redoubt. So this is looking back over just about a year. The eruption is here, and again you see the same thing of the seismic unrest. So fortunately 2009 had a little longer precursory period, about 6 weeks, than the 89, but still this weird thing of the first earthquakes are shallow. And in this case there was an additional clue. So some geologists were out doing field mapping on the volcano the summer before, and walking around on the summit of the volcano, they noticed this very strong rotten egg smell. So this is hydrogen sulfide. And so remember that gas starts to come out of a magma only when that magma has made it to fairly shallow levels. So this was an implication, kind of confirming our best guess for why this pattern occurs, that magma has already made it up here, even though it's not producing earthquakes. And so potentially we might be able to use some seismological tools in this period where we don't have earthquakes coming from the volcano, but we might be able to sense that magma in other ways. So the analogy I wanted to give to you for this problem and our solution is one that unfortunately I've encountered, and I'm sure many others have, is you wake up one day and you have a toothache. Your tooth is kind of throbbing. And so you cancel work and you go to the dentist, and you have a giant cavity and you have a root canal. Okay? So this is your tooth throbbing and this is your root canal. But if you do what you're supposed to, and I won't say, and you go and you get your preventative X-ray every 6 months, the reason they do that preventative X-ray is because if they can see that cavity when it's still small and not as progressed, it's a lot easier to deal with, right? It's probably a lot less expensive and painful. So this is kind of what we're trying to do. You can still fix the cavity with this much warning. You can still fix the cavity with this much warning, but ideally you'd not want to have to deal with that root canal. So X-rays are important. Everybody go to the dentist. Call them tomorrow. So this is exactly what we did. We decided to X-ray the volcano during this period. And the way that we did this X-ray is by using tectonic earthquakes resulting from plate motion, as our X-ray machine, as our X-ray source. And then the seismometers on the volcano acted as a little bit of film they stick in your mouth. And then, so we're trying to look at the tooth here, which is the rock beneath the volcano. So we have these rays of energy produced by the earthquake that are passing through this volume of rock, and we can image them. Even though there's no local seismicity, we can see what the state of this rock is. And specifically what we're looking for in this study is whether that rock is being compressed in a way that's consistent with magma entering this region. So we're not looking for cavity. My analogy falls apart here. We're not looking for little holes. There are techniques to do that, but in a volcano like Redoubt, it's probably too small to see unless you have a whole lot of instruments. But that compression from a little bit of magma is probably going to affect a fairly large volume, so we can look for that compression. And the way we do that is using an analysis tool that was actually developed several decades ago, in part at DTM at Carnegie, to study larger scale structures on the Earth. And this is known as shear wave splitting. So the idea of shear wave splitting is that a shear wave of energy, so a vibration that's a shearing motion, passing through a volume of compressed rock will be distorted in such a way that that shear wave is reoriented or polarized in a direction that's consistent with the direction of compression. So basically what we're going to look for is this orientation over time before the seismicity. And bear with me, I'll walk you through this because this is a lot to have on a figure, but what I'm showing you up on top here are circular histograms showing our measurements of that polarization direction, our X-rays. So in this setting, in this part of Alaska, the signature of volcanically induced compression would be a northeast-southwest orientation. So what we're looking for is these rays to go to a northeast-southwest. So the first thing we did was look at a background period. So the volcano was asleep. We figured nothing would be going on. Let's see what the orientation is like there.
And so that's this here. And so you can see that the orientation we got during the background period is northwest-southeast, totally inconsistent with volcanic as we expected. But then as we move into this precursory period, we see sort of a transitional period here around the same time that the gas smell was detected. So there's still that northwest signal, but maybe a hint of this emerging volcanic signal. And then stepping through time, well before the seismicity kicks on, it becomes very strong. Okay, so this here is a strong signal of magma pushing the rock aside, even though it's not generating earthquakes. So the point is that actually, yes, consistent with our best guess at why we see this top-down seismic phenomenon and the fact that gas was sensed so early, this new seismological tool basically confirms and tells us that, yes, this whole period there was a subtle precursory signal there that was indicating that magma was ascending. There was a gas measurement at this point, but we don't always have those. In Alaska, they're very hard to make. So being able to do this sort of analysis with the seismometers that are on the volcano for monitoring local seismicity is really a huge benefit. So basically the takeaway from this part of the talk is that the shear wave splitting analysis can detect stealth magma ascent and give us much earlier eruption warnings, which is particularly important at volcanoes that have short seismic run-ups, like 1 week or 1 day. Okay, so this is an example of looking in a quiet period and finding a signal. So the next story that I want to tell you is actually about the quiet itself being an important signal and containing information. So for this story, I'm going to turn to a volcano you heard and saw a little bit about in Matt's video, which is Tolica in Nicaragua. This is one of my favorite volcanoes. It's a place I've been working for years, basically because it's an excellent laboratory volcano. It's what we call a persistently restless volcano. And what I mean by that is that it sits right on the cusp of being about to erupt and in eruption, and it periodically tips back and forth. So it's a great place for us to study transitions into eruption. So it has anywhere from hundreds to, on occasion, 1,000 low-frequency, very, very white, is very much present at this volcano, events per day. So it's right at that edge of erupting. And then it periodically tips into eruption. There have been eruptions recently in 1999, 2011, 2013, and 2015. So what you're looking at on the bottom here is a very simple figure for the incredible amount of work that has been done by a lot of people to make this study happen. So we've had instruments tracking the activity of this volcano since 2009. And basically, we've been counting the number of events, seismic events per day. The blue are the low frequency, and the red are the high frequency. So it's incredibly variable, and I think we've recorded something like 500,000 earthquakes at this point. So it's a rich data set, and it's a great place to work. And I work on a bunch of different questions here. But the one I want to talk about is something that we noticed during the 2011 eruption, which was a really small-scale eruption, but actually one of the types of eruptions that's now one of the most dangerous, and these are called Phreatic eruptions, and they don't have a known warning. They're basically steam explosions. There was one at a volcano in Japan called Ontake a few years ago that unfortunately happened without warning while hikers were on the volcano. So we're really interested in anything we can find to predict these small phreatic eruptions, and this is what Tolica does. So one of the things that we noticed during this eruption sequence, this series of explosions, was that right before the explosion, so here's some seismic data from Tolica, right before the explosions, so this is an explosion here, you can kind of see this like long-term sustained vibration, and we correlate these with pictures in some cases, so we were certain that they're explosions. The volcano gets really quiet seismically. Normally it has this high rate of long period, low frequency events, but right before the explosion, it just completely quiets down. And so we thought, that's interesting. Let's go through the entire, we had 50 explosions in this sequence over a month. Let's go through and see if this is something that happens consistently. And so we mined the data and looked at that, and here's a few more examples. And it turns out that all but 2 explosions in this sequence had this detectable quiescence. So this is a remarkable rate of false negatives. We pretty much could have predicted every single explosion except for 2 when we observed quiescence. And we do some processing to pull it out better of the raw data, but you can even see it really nicely in the raw data. So here's the explosion, here the quiescence, and so on. So this is a very reliable phenomenon, precursory phenomenon to these individual explosions. So that was quite exciting. So the other thing that we noticed as we were going through this was that these periods of quiescence are actually quite variable in how long they last. Sometimes they seem to only go on for minutes. Sometimes they went on for hours. And one of the things we know about volcanoes in general is that sort of the longer a volcano has been dormant, typically those are the volcanoes that produce the biggest explosions. So for example, Pinatubo, which produced the second largest explosion of the 20th century, had been dormant for millennia. And typically volcanoes that have erupted recently don't produce large explosions. So we wondered if that might actually be something that scales down to these individual events. So we decided to measure the duration and see if it was consistent with how big the explosion was. And apologize in advance. These are the only two equations. To do this, we needed a way to quantify the duration of the quiescence, which is pretty simple. It's just when did it start and when did it stop and how long did that last. But we also needed a tool to quantify the size of the explosions. Again, these are pretty small scale, so doing things like measuring the column heights or how far rocks were thrown wasn't really a very useful thing. So what we're doing here with this horrible looking thing is basically using the seismic data to tell us, to give us a proxy for the strength of each explosion. And all we're doing is we're just integrating. We're kind of adding up over the time when the explosion was occurring to get a proxy for energy that we can at least use to compare the explosions to each other. And when we compare quiescence duration to explosion energy, the correlation is remarkable. Small, short episodes of quiescence duration are generally followed by small eruptions. And the largest eruption in the sequence in terms of energy release was the one with the longest quiescence. So this can be a predictive tool. Basically, we can say if the volcano has been quiet for X amount of time, the minimum explosion energy is this. So this is the takeaway. Longer quiet periods predict larger explosions. Those of you with small children in the audience may recognize this phenomenon. Your kids are playing in the other room. You realize you haven't heard them in a while. The longer it's been, the bigger a mess you're going to find. The volcano works the same way. The longer it's been quiet, the more trouble it's going to cause. Okay, so these 2 stories that I told you were about finding a new type of precursor, a new signal, something we didn't know to look for beforehand. And the last story I want to tell is a little bit different in that we kind of know what we're looking for, but we need a better tool for finding it in the data in real time. And this is fairly new work. The paper's still in the publication process, but it's been a lot of fun because it was one of those, like, I had a really crazy idea, let's just see if it works, and it worked like beyond my expectations. So sometimes you get lucky. So this study was at a volcano called Popocatépetl, which is just outside of Mexico City. It's an extremely active, very large volcano. It's been in eruption since 1994, and what that means is that basically it has explosions more or less continuously, several per day, but sometimes it'll go through a few years of being a little quieter, smaller explosions are less frequent, and sometimes it'll go into a phase of having larger explosions. So we would like tools to be able to predict the larger explosions. And one of the nice things is that we recently saw an increase in activity. So several years of very large explosions starting in 2012 and really still kind of picking up, still going through. There were just some last week that were quite large. So we know that many of the major explosions of Popocatépetl are preceded by a signal that we call harmonic tremor. So what is harmonic tremor? Harmonic tremor in general is a sustained ground vibration. But there are several types of tremor that we see in our seismic data at volcanoes. So there's just broadband tremor. So this is an example of it from Kilauea, Hawaii. So you're seeing the time representation. You can see it's just kind of bouncing all around. And it doesn't have a whole lot of structure in terms of where the energy is. So if I were to play this for you, it would sound like static. And then this is harmonic tremor. It's a really cool signal to look at. And you can see how much more structure it seems to have in it. So this is from one of our stations on Popocatépetl. And if you look at it in the frequency domain, what you see is that it has these bands. So it has a fundamental frequency and overtones. And this is characteristic of sound, of human speech, of music, of basically resonance. So we're looking for this signal because we know that it's a very reliable short-term precursor to eruptions. So here are a few examples. The first time it was detected was before an eruption at Nevado del Ruiz in Colombia in 1985. I'm sorry, the plot is not very good here, but this is an important one because it's the first time we've recognized it, and it was a very large, devastating eruption. And then here's a more modern example from before an eruption at Redoubt, the one I talked about earlier, where you can see these bands in the data, and this is leading up to an explosion. So it's a good short-term precursor to major explosions. The problem with harmonic tremor is that it's very hard to automatically detect in data. So most of our algorithms for processing seismic data look for very sharp changes. So we'll look for something like this high-frequency earthquake where the amplitude of the signal is small and then all of a sudden becomes big. Harmonic tremor, in contrast, kind of emerges out of the noise. So it doesn't do very well with our routine algorithms. But I got to thinking about these commonalities between harmonic tremor and sounds, and also about my phone, which I yell at actually most of the time. Siri, I'm lost, help me. And how that actually works. So there's been this wealth of development of tools to process speech and to automatically process music. And I got to thinking about what could some of those be adapted. So we used a very simple, one of the simplest tools or challenges in speech recognition or music recognition is pitch detection. So pitch is the fundamental frequency. And you need to detect pitch and then build a more complex algorithm around it, whether you're looking, for example, for intonation in speech. Are you asking Siri a question, or are you telling Siri something? Or are you looking to find a word in a tonal language like Mandarin? So pitch detection is a very commonly used tool, and there are several algorithms for doing it. We used a really simple one that basically goes through each minute of data and finds the pitch, whether there's tremor or there are not. And based on that, we can build an algorithm that basically assesses the shape of what's called the periodogram of the signal. So this is a new representation you haven't seen before, where now I have frequency here and I have power. And so you can see this is harmonic tremor, and you can see it has this really distinctive structure to it, whereas non-harmonic is kind of noise. So we can basically figure out automatically, does it have this shape? And it turns out to work incredibly well. So we're still, again, just at kind of the end of this technique development phase. But here's kind of the first result, which is actually using it on Popocatépetl data. So this is now 6 months of data at Popocatépetl over an extremely active period. And what I'm showing you now is sort of the cumulative number of harmonic tremor minutes, so the minutes where we see this tremor. And then these triangles here are where we had major explosions. And so this is all done purely automatically. Normally it would have been done by hand, if at all. So not only is it very computationally efficient, but it's also consistent. So you don't have different analysts with different ideas about how to do this manually, and changes in the data are the result of, the guy who comes in on Friday has a different way of doing it. So the great thing about this is it shows us very clearly what we know is happening, which is that increases in harmonic tremor precede the explosions. And then we have a quiet period, increase, explosion, quiet period, increase, explosion, quiet period, increase, explosion. So this is a tool that can do a much better job, more efficient job, of a complicated data processing task to look for a signal that we're aware is there, but we need a way to pull out. So it's sort of a different thing, but the takeaway from this is that this is a sort of a first attempt at trying to apply speech and music recognition technologies to volcano seismic data based on this shared similarity between some of the seismic signals that volcanoes produce and things like human speech. All right, the last thing I want to talk about, I just wanted to end with some comments and maybe some suggested reading for people who are interested on where I think what we think the future of eruption forecasting will be. And I'm going to name a couple of efforts that I'm not involved in. They're driven by the United States Geological Survey and the Smithsonian Institution, so if any of those folks are in the house, well done. Really, a big thing that we need is greatly expanded monitoring networks. So you've seen examples of what we can do when we have instruments on the volcano, but most of Earth's volcanoes are woefully unmonitored, under-monitored or completely unmonitored. So we need to expand those monitoring networks. And in the United States, there's a proposal from the United States Geological Survey called NViews, the National Volcano Early Warning System, which is basically a proposal to bring all of the United States active volcanoes up to state-of-the-art in terms of the instrumentation that's being operated on them. Another key step, and one that's been in process now for decades, and the Smithsonian Institution has really been leading the charge on this, especially in recent years, is the development of databases, basically of symptoms. So this is what some of my colleagues have referred to as volcano epidemiology. So basically what we're doing in forecasting eruptions is taking a pattern recognition approach. So, okay, we typically see this pattern and that's what happens. But at a volcano we haven't seen erupt before, we want to be able to reference, okay, other volcanoes, when they do this, what happened? So databasing all of these observations in a searchable way is really important to us because that's basically, we look for examples. Okay, where has this happened and what did it lead to? As a key way of forecasting eruptions, particularly at unknown, poorly known volcanoes. And then the last one is a shift from this pattern recognition approach to more of a physics-based modeling approach. So the analogy here is to weather forecasting. So for millennia, weather forecasts were done based on pattern recognition. So the adage that a red sky at night is a sailor's delight, it means that the storm is past, where a red sky in the morning is a sailor's warning, the storm is coming. That's a pattern recognition. Whereas now, weather forecasting involves supercomputers doing complex computational fluid dynamics, ingesting vast amounts of data to calibrate them. And that's really where we need to be with volcanoes. And we're a long way from this yet, but there are some early efforts to move away from the pattern recognition and into something that is more of a physics-based model. So that's basically my final point. There have been a lot of successes. This is why it's an exciting field, but there's still a long ways to go in eruption forecasting and a lot of potential, and I think a lot will happen over the next 20 years or so. And I'm very excited to watch that and hopefully be a part of it. So last but not least, any scientific endeavor is the work of huge teams of people. The one person standing up talking to you, but everything I've shown you tonight has been because of the effort of lots and lots of colleagues. And so I want to thank these individuals in particular, as well as my observatory partners in Alaska, Nicaragua, and Mexico, as well as the various agencies that have funded my research over the years. And I'd like to thank you for your attention, and at this point, I think we have some time for questions. Thank you.
So we have microphones here and here for questions. We'll switch it up. You can invent answers, and she'll try to guess the questions.
Yes, please.
You didn't emphasize anything regarding the viscosity of the magma and the effects on seismicity. Anything neat?
I could give a whole nother talk on that one. The short answer is, so some volcanoes do this bottom-up propagation, like Piton de la Fournaise. All the guys that do that are basaltic, low-viscosity magmas. Iceland does it, Piton de la Fournaise does it, Hawaii does it. When we see that that nice what we expect pattern, it's at a volcano with low viscosity magma. All of the top down is higher viscosity stuff. And so that's one very intriguing correlation, is that we do seem to see a difference in how seismicity is produced that might be related to the viscosity and the speed at which that magma can move through the crust. That's a great question. Thank you. Over on this side, please.
You mentioned using highly sensitive instruments to monitor gas emissions, and you mentioned taping that instrument to a helicopter. Do you see any demand for unmanned systems, autonomous drones, being a more cost-effective way to monitor that activity?
Yes, and this is happening. It's actually one of the biggest explosions of activity in the field. People are now using drones to monitor gas, to take high-resolution video when there's a look angle that we can't get on our own or where it's too dangerous, and also using those videos or photos over time to find changes in the crater. So drones are a huge, huge technology for volcanology and volcano monitoring, and everybody's still trying to figure out exactly how to do this. But yes, absolutely, that is an important next step, and it's in the process of happening. Yes, please.
Yeah, thank you very much for your talk. I just had two questions. One was the question of false positives in these seismic data and how big a problem that is and how that's handled in a real sort of prediction sense. And the other is if you could just talk a bit about the physics of why there's the increase in harmonic tremor.
Okay. Those are two talks each. The first question is about false positives. The first question was about false positives. I mentioned false negatives when I talked about Talika, but false positives are in fact a huge problem for us in volcano monitoring. So a false positive is basically, an example of this would be we'd see a big seismic swarm and nothing would happen. And actually, again, we don't have the data yet. It's just there are some people who are starting to do the statistics on this, but we think that's actually far more common than that seismic unrest proceeding to eruption. We see a lot of false alarms. And at this point, we have no way to distinguish. A start of a swarm that's a false alarm to us looks identical to the start of a swarm that proceeds to eruption. So this is a big open question in volcano monitoring and a very difficult one. And many people working on it. Question 2 was about, physics of harmonic tremor. Okay, so this is it's an organ pipe. So imagine a crack in rock with gas flowing through it. So that gas is going to set up a vibration in that rock. And that's, hopefully none of my colleagues are, this is something we fight about a lot. But, and a lot of the fight comes down to, okay, what is the shape of the crack and what is the fluid going through the crack and, kind of nerd level squabbles. But most of the models, most but not all, boil down to this simple organ pipe type thing of you're pushing a fluid through a solid, and just like how musical instruments work, you're setting up a resonance, and if that gas flow is sustained, that resonance will go on and it will have harmonics depending that actually correspond to the shape of, and this is one of the things that we're trying to study at Popocatépetl is, does the harmonic tremor correspond to the amount of gas coming out of the volcano? What is actually the process? So this was the first step towards that question. That's really why we went out there. So this side, please.
I have two quick questions.
Yes.
One is, what did you think of Werner Herzog's film Into the Inferno?
I just watched that.
And second, when you were growing up, did you do a science fair project consisting of building
baking soda volcano?
an artificial volcano like in the Brady Bunch?
In the Brady Bunch? I don't remember that one.
There's an episode of, it's
Okay,
good.
I'll
You
put
get
that
on
on
YouTube.
I'll put that on my watch list. Yes, so Werner Herzog made a documentary a couple years ago that's called Into the Inferno. It mainly follows a British volcanologist named Clive Oppenheimer, who's primarily a gas specialist. He works a lot in Papua New Guinea and Indonesia. It's a fantastic documentary. It's on Netflix or Hulu. Netflix. And I highly recommend watching it if you'd like to see sort of the life of a volcanologist in the field. Did I do projects? Yes, of course. I loved science as a kid, and I loved to make a mess and play. And I'm sure we did others, but I remember the baking soda volcano. I'm old enough that it was pre-Mentos and Diet Coke, but we did the vinegar and baking soda, and Mom would come in like, yeah, mess in my kitchen. So yes, and those are great experiments. Yes, this side, please.
Thank you for your lecture. My question pertains to planetary science's role in terrestrial volcanology. Volcanology grew as a field in the 20th century as the mariners and Viking orbiters discovered the correlation between a volcano's size and shape and the level of gravity. The Pioneer and Voyager probes similarly discovered tidal volcanology on Io. But there was also this outlier of nitrogen plumes on Triton, discovered by Voyager 2. Now in the 21st century, when we have potential candidate sites for cryovolcanology on Titan, discovered by Cassini, and Pluto, discovered by New Horizons, do you think that the field of cryovolcanology will offer insights into its hotter analog?
Ooh. So this is not my field, and I actually don't know a whole lot about cryovolcanology, but I guess the answer I could give is that we're always looking for analogs. So we're looking for toy volcanoes. It's easier to understand a system and how it works when you can kind of strip away some of the details. So each volcano has a personality. And we kind of want that personality out of the way so that we can see the common process. And so many of my colleagues have looked at things like geysers or mud volcanoes as very simple analogs for hot volcanic systems. And cryovolcanism might also be an analog as well. But again, this is really not my field, so I'm not very aware of the connection between those two. There certainly are people who are interested in both and using information from planetary volcanism to understand Earth and vice versa. Yes, please.
My question is about the broadness of data that you can accumulate that would be useful to your predictions. Is there anything comparable to, say, for example, in the weather with Doppler, or can you do animal behavior? In other words, how much information can you plug in to not only get a local picture, but to get a planetary picture?
Well, and actually I think I heard a previous speaker in this lecture series make this point that we have too much data, but we have not enough data. We're drowning in data, and as you saw in my last example, we're trying to find ways to just deal with that fire hose of data that's coming, especially from continuous networks. And we're always looking for anything we can pull in that's additional information, whether it's meteorological data or, in some cases, biological data. But one of the big challenges in volcanology has been in integrating these different data streams, which is it's great because you need a model that explains what the gas is doing, what the seismicity is doing. But at the same time, it's very challenging because often those data streams are taken at different sample rates, so you don't know whether they truly correspond. But we know that ultimately, multi-parameter studies of volcanology are what help us to fully constrain our models. And so I'd say the sky's the limit. I mean, we're always looking for anything we can get when we're out in the field. I mean, I study seismology, but whenever I'm out on one of my volcanoes, anything I can learn about the hydrology of the volcano or the geomorphology is also critical information that I keep and try to integrate into my studies. Thank you. Yes?
I have two questions. First is, given that Earth is about like halfway into its lifespan, is that any guarantee that large mantle plume events such as second traps will like never happen again?
So I believe the question is that is there a possibility of an eruption on the scale of the Deccan Traps, a large igneous province?
Given that Earth is like halfway through its lifespan.
Okay. I don't think we know about the probability of a large igneous. So a large igneous province was like the extreme of my disaster graph at the beginning. So these are flood basalts. They're basically massive, massive outpourings of basalt that are thought to significantly affect climate on a global scale and possibly mass extinction. So the Columbia River flood basalts is another more local example of these. We don't know much about these events or the super eruptions and really how likely they are in our lifetime or in the rest of Earth's history as a planet with active plate tectonics. We don't know what they'd look like if they were coming because they're very hard to study. We have very few examples, and many of them are so far back in geologic time that we only have limited information. So that's a big we don't know. I don't know. And your second question?
Does your research go into, so for volcanoes that have lahars on the top of hazards, like do you typically research how much? I hate this.
Your question, it sounded like, was about do I work on volcanoes that have lahars and pyroclastic flows?
Yes, like specifically, how much of, say, like a snowpack would melt in a lahar event? Again,
so how much of the snowpack would melt? So that's again a bit out of my field of study. So many volcanoes have glaciers on them, and a big hazard, particularly for snow-covered volcanoes or volcanoes in tropical regions, is that the material from an eruption will mix with that water and create a hot mud flow called a lahar. I don't work on these, but we know that they're quite common. Popocatépetl has had lahars during its rainy season. Pinatubo had lahars because the eruption occurred during a typhoon. So this is a major hazard and certainly a major focus of interest in volcanology. How do we predict these lahars and their path? And actually, seismometers are one of the ways that we monitor if a lahar is coming. So there's a big hazard from Mount Rainier in Washington of lahar, and part of the system for lahar detection and warning is a series of very small seismometers that might be able to sense the ground vibration from that lahar as it comes through the river channels. Yes, please.
Wondering if the worldwide seismic monitoring network provides any useful hits to send down a SWAT team to do what you do, for example. And I'm wondering if there isn't a fourth technique, which would be a real-time acoustic or seismic tomography of the volcano.
Yes. Yes, and I alluded to that very briefly talking about our X-raying of Redoubt. So if we were actually looking for the cavity, the hole with magma in it, we'd use seismic tomography to see if we can actually see that volume of magma. And so far, efforts to do this have only worked at the largest volcanoes, so Yellowstone, which has a massive chamber. It doesn't tell us a whole lot. Seismic tomography so far doesn't tell us a whole lot that's useful in the forecasting sense because it's very difficult to do rapidly enough to sense a volume of magma coming through. But it is integral to our understanding of the structure of the subvolcanic plumbing system. Your first question?
Wondering if the nuclear bomb seismic monitoring ever provides a useful hit, despite the fact that the events are much lower frequency.
So the GSN is a global monitoring network of seismometers that are used for detecting nuclear tests. It's part of the CTBTO efforts to search for nuclear testing. And those seismometers are also integral to studying and recording large tectonic earthquakes. They're generally too far away from volcanoes to do us much use. I think there are a couple that are proximal. But the earthquakes that we deal with are so small that really, if my seismometer is not within 10 kilometers of the volcano at maximum, I'm not going to see much. So the regional seismic networks, unfortunately, are not very useful to us. Thank you. And one last question, please.
Last one. Thank you. Wondered if you saw the video of the tourists near Mount Etna in the most recent explosion. And I saw that you have in one of your graphics, it looks like you visited either Etna or Vesuvius or both, and if you would remark about how that's an example of them not knowing that it was going to erupt.
Well, so I did see the video, and this is a video that came out a month or two ago of actually journalists who had gone out on Mount Etna, which is on the island of Sicily in Italy, with some of the local scientists, and they were caught in a really scary explosion. This was an explosion that was the result of a lava flow interacting with snow. So this is actually similar to the types of explosions we have at Tolico, which are phreatic. They're steam explosions, and they're very, very hard to predict. So it's not surprising to me that they were caught out. That was a very dangerous situation, and really lucky that nobody got hurt. And certainly a demonstration. Etna is one of the best monitored volcanoes in the world with some of the best scientists. One of the examples of how a volcano can still throw surprises and why we need better monitoring tools. So yes, it's a very good video to watch. Okay, thank you everybody.
All right, thanks everyone for coming. We've got another talk coming up on neuromorphic computing by Quaban and Bohan, which will be fascinating, I guarantee it, this one. So join us for that. Be safe.